Welcome, welcome. So the first item of business is to embarrass Cian. My co-founder Cian Amodine and myself set up Nearform 5 years ago at this stage. This conference and all the cool stuff that we happen just worked because Cian convinced me to borrow a lot of money back in the day. But look how it worked out. It's awesome. It's really cool. And we really look forward to this time of year because we bring all the really cool Node people together. And it's one of the, I guess, the highlights of the year for us because it's really an expression of the culture that we care about. So I just want to say thank you again, Cian. It's absolutely an awesome conference. Okay, serious enterprise stuff now. Yeah, we started working with Node about 5 years ago. We built a whole bunch of monoliths, and like Machi was just saying, that kind of doesn't work with Node unless you're really, really good, and we're not. So JavaScript, the language, doesn't give you a whole bunch of constructs for creating components and that sort of stuff. So you end up going down a microservice path when you build big systems anyway. And we've been building Node.js microservice systems for a couple of years, and we've done everything wrong. We've done all the different variations, tied ourselves in knots, put everything in one big mono repo, put everything in a whole bunch of different repos, use HTTP for comms, use a message bus, all that stuff. So when I talk about this stuff, it's kind of from the perspective of learning from our mistakes, as opposed to saying, this is the one true way. It's more an expression of what we've discovered in practice. My first question is, put your hand up if you have knowingly deployed software that you know is going to fail in production. Yes, that's actually a good percentage. That's better than most. The interesting question, and the thing I want to talk about today is the other scenario when you think things might work, but you don't know and you're not sure, and your boss is standing over your shoulder going, "Come on, deploy," and you're like, "Maybe this is a good bet. I don't know." When do systems fail? So I want to talk about 3 Mile Island. So 3 Mile Island was a nuclear accident, the worst nuclear accident on US soil. It occurred in 1979. The second reactor, and if you look at the picture here, it's the reactors of the big cylindrical buildings. The second reactor suffered a partial meltdown and a partial release of radioactivity. And there was obviously afterwards a big investigation. So the President's Commission was formed to look at what happened. And in these types of systems failure scenarios, people often ask what seems to be a valid question, which is, what is the root cause? Right? So, do your 5 whys analysis. Ask why 5 times. That President's report started pointing the finger of blame at the human operators on the day, the design of the system, the maintenance, also the company that built the reactor. But in reality, you have to wonder, is asking that question, what is the root cause, valid? So let me give you a software engineer's perspective on nuclear power stations. Boxes and arrows. Right? So this is a highly simplified explanation of how nuclear reactors work. You've obviously got the reactor with uranium. It's giving you lots of heat, which is heating up water that you use to drive a steam turbine. The water in the reactor core is high temperature, high pressure, and it's radioactive. So you can't actually drive a turbine with that water. So you do a heat exchange. The radioactive water heats up pure water, which is only high temperature and high pressure, And that drives the steam turbine. And that's the basic structure of a nuclear reactor. It's an extremely simple architecture. The problem is all the hidden components, all the devil in the details. And that's where it mirrors software systems, because failure occurs in all those subcomponents that are just as important as this simplified diagram. Now let's look at how the accident actually happened. So the pressure valves, the valves that control all of the pipes in a nuclear power station, need to be very strong. So you use air pressure to drive them. Now, the water that turns the turbine is turning precision-engineered blades. So that water has to be very, very pure. So the water is purified by something called a condensate polisher. The seals on the condensate polisher leaking a small amount of water vapor into the air pressure system, which caused the valves of the primary coolant pumps to fail, because you're not meant to have water vapor in your air pressure system. But that's okay. There's a backup. There are secondary water pumps that are meant to prevent failure in the scenario. Except that during maintenance 3 months previously, some of the valves for the secondary cooling system had been left closed. Now you may think, oh, definitely maintenance error. But then think about it. There are 500 valves minimum in these plants. How many times have you walked out your front door and you can't remember whether you've locked the door or not? This is an expected human failing. As a result of no water coming in, the system started to overheat. And unfortunately, that means that the water inside the reactor got to even higher pressures, and the steam got to even higher pressures. Now, that's a failure scenario because the containment vessel could burst. So you have another automatic safety device, a pressure relief valve. Now, this valve is for high temperature, high pressure, radioactive water. And if you think about it, designing a valve, a mechanical system that can handle that type of thing is pretty hard. In fact, those valves are rated to fail 1 time in 50. You may think that's completely unacceptable for a nuclear power station, but there are limits to our technology. You just can't build valves that are any better. So the valve opened, the pressure relief valve, and failed to close. Now, think about what that means. That means that the coolant water, which has already started to boil away, is now leaking away. The indicator light in the control panel also failed. So the operators didn't know that this was happening. Of course, the system started to go completely haywire, so they used another automatic safety device, which is the injection of high-pressure cold water into the containment vessel. But you can't do that forever because you'll crack the containment vessel and you'll have a loss of containment accident anyway. So the operators dialed back the injection of water. So you had a small amount of water coming in and a large amount of water going out. The uranium was exposed and there was a partial meltdown. And the situation didn't actually get under control until about 2.5 hours later, when a new shift came on board and new people were there with a new perspective. So now I ask you the question, what is the root cause of this accident? There isn't a root cause. The complexity of the system is so overwhelming. It's the complexity itself that is the cause of this accident. And this type of complexity is inherent to complex systems, and it's inherent to the software systems that we build. So let's step back and see, can we model this idea of complexity in a really, really simple way. So here's a really simple software system. It has 2 components. Both have to work for the system to work, and the components fail independently. So you can use very, very simple probability theory to work out the probability that the system will fail. If each component is 99% reliable, the system has a nearly 2% chance of failing overall. So not a 99% success rate, but a 98% success rate. Your intuition about failure often lets you down. You tend to think in terms of the slowest ship in the convoy. It doesn't work like that at all for complex systems. And in fact, if you chart it out, if you have a system with, let's say, 50 components, each 99% reliable, overall, the system has a 45% chance of failing. And if you think about software systems, they have lots and lots of components. Now, we do have an obvious way to make systems better. Redundancy, right? So you have backup systems. And you can see that, of course, backup systems, like in 3 Mile Island, often cause their own problems. But in software, the redundancy from backup systems is not as good as you think. It's not as useful as the physical systems. And that's because the redundant deployments, the multiple instances of individual microservices or monoliths, are homogeneous. They're the same version for the most part. So that means if there's a bug in one instance, the bug is in all instances. Now, obviously, this is modulo, power supplies failing on individual physical machines. But those types of failure scenarios occur much less frequently than software bugs. So redundancy, while it gives you the ability to handle load, does not give you the ability to handle failure, per se. And now think about what a monolith deployment looks like. A monolith or a microservice system is simply a whole bunch of components interacting together. This is a simplified component diagram of 3 Mile Island, by the way, massively simplified. When you do a traditional monolithic release, you're actually taking a whole bunch of components and changing them at the same time. So the probabilities work against you in a horrible way. And if you think about monolith deployments, especially in business-critical systems, they're often done at the weekend. Why? How many people have spent weekends trying to get systems up and running for 9 a.m. in the morning? Right? So think about what happened. At 6 p.m. on Friday, you're into deployment mode, and you deploy the first version, and something breaks, change config, you keep messing around. What were you doing all weekend? Continuous delivery. Instead of doing continuous delivery over the prior 6 months in a stress-free environment, you just moved from a waterfall, highly controlled, QA-based approach to 2 days of rapid, intensive development under continuous delivery. So you just did continuous delivery anyway. Why not do it over 6 months and not stress yourself out? This comes from a fallacy of perfectionism in software development. The most perfect software system that I've been able to discover is the Space Shuttle Control Computer. And it had the people who built that system, who were 50% female, by the way, they had one bug every release, on average, over 450,000 lines of code. But the cost of building software that perfect was $1,000 per line of code. Now, the ROI on that just doesn't work. But how many enterprise software projects have you been on where there is an implicit expectation of perfection? It is politically dangerous to admit that there are going to be bugs. There's this whole waterfall pipeline of gating and QA and business requirements analysis and all that sort of stuff. And everybody behaves as if bugs are unacceptable. You may not have any bugs at all, and it's unprofessional to write bugs. But the problem is, if you speak up, that's it, career-limiting move. So the problem we have across the industry is this idea of perfectionism, which doesn't match reality. What you want to operate is, you want to operate in a completely different way. You want to accept that there are always going to be errors in your system, and you want to stay below the number of acceptable errors. You want to be able to do lots and lots of small deployments that may break small amounts of things, but don't break the whole system, as opposed to a low frequency of deployments that cause catastrophic failure. This is how you stay sane. Very small changes, no stress. But the problem is, most of the time, we're doing changes infrequently, changing lots of components at the same time, and of course they fail. It's a bad bet. The place you want to be is a good bet. Who plays poker? Okay, is this a good hand? Right, 4 of a kind. It's a pretty good hand. I mean, it won't beat a straight flush, but it beats most hands. This is the place you want to be. You want to have a reasonable degree of confidence that when you deploy things, they're going to stay below the acceptable error rate for your system. You can't have perfection, right? Some percentage of requests are going to fail. But if everybody, including management, accepts that there's an acceptable error rate, you can use this idea to make sure that your system stays up, that you remove and quantify risk. It's very difficult to do with a monolith because you're changing large parts of the system at the same time. Much easier with microservices. This is where you get your payoff, the additional deployment complexity, the additional management complexity, the additional network complexity of microservices give you a payoff because you can make risk quantifiable. You can manage risk in a much easier way. The probabilities work for you because you're only deploying and changing one component at a time, not lots. And it gives you a number of deployment patterns that just fall out of your Terraform scripts or whatever. You don't have to build entire deployment systems. So when I worked in Feed Henry, for example, we built, and it took us a couple of months to build a complex, competent blue-green deployment system. And yes, that helped us do our quarterly releases, but it was a lot of work. With microservices and microservice deployment automation, you get all that sort of stuff pretty much for free because you control it anyway. So here are a couple of deployment patterns that you can use to control risk. One obvious one is a canary. So let's say you have 10 instances of microservice A at version 1.0, and you want to upgrade it to 2.0. So into my live running system, I add a new instance of microservice A at version 2.0, and I see what happens. Does it break stuff? I'm only directing 1/11 of my traffic through this new microservice anyway. If it does break, and in the example here it does break, I just roll back. I take it back out. So I don't have to build a system for doing canary deployments. I get it for free as part of my microservice deployment system anyway. If the canary actually worked, then I can move to using a new pattern, which is the progressive canary. So you don't just say, OK, one instance worked, let's just deploy the lot. You progressively reduce the number of instances of the old version and progressively increase the number of instances of the new version. Always monitoring, always checking what's broken. This means that you can safely transition with zero downtime from one version to another. Now, this reduces your risk significantly. And you can even do things which allow you to handle systems that have very, very sensitive data. Who uses GitHub? Yeah, come on, no, put your hands up. Everybody put your hands up. So what do you think would happen if some of the proprietary code that you were working on for customers or for your company, if when I went to my GitHub account, I suddenly had access to your repositories because GitHub had a bug in their access control system? That would kind of suck for GitHub and for us. But yet, we know for a fact that GitHub does continuous delivery and deploys stuff at a rapid pace. How do they control against this risk? There is actually an article written by Zach Holman where he goes into how they manage it. They don't use microservices, they use feature flags. But the essential idea is that you run the old and the new side by side, and you bifurcate the traffic, duplicate the traffic, and you throw away the output of the new system. So it doesn't have any effect. But before you throw it away, you compare it against the old system to see if there are any variances. And you do that for a week or whatever, and you can then have a good measure of the risk of the new system because you've been running it against production traffic, and you've been ensuring that your business rules, access permissions, etc., are being observed. Now, in a microservice context, that becomes a variant of the progressive canary. And you just manage the flow of messages between microservices to ensure that messages emanating from the new version are thrown away after you do this comparison. And those, so I've just shown you 3 patterns, and there are lots more, because you have a system that is very, very easy to control and very, very easy to put into different configurations. So microservice deployment and a continuous delivery model under microservice deployment can be viewed as a risk measurement device, because at each point of your deployment pipeline, you can estimate the probability of failure. You can estimate the probability that this individual microservice is going to cause your error rate to go above the acceptable level. And at each gate, from the developer's laptop to build, to staging, to production, you can have an estimate of this failure probability. And all that the continuous delivery pipeline does for you is quantify the risk. And this is the formula that you use. So you have to learn how to use this formula. No, you don't. So this gives you the this would give you the probability estimate using that simplified model that I gave you before. And if you wanted to get real estimates, you could start using Bayes' theorem, and you could start doing Monte Carlo simulation, and you could get very, very fancy. But you don't need to, because your brain is already running these calculations for you. Your brain already assimilates knowledge and understanding about the system that you're running. Machi, in his head, has an intuitive grasp of the failure scenarios that the NPM registry can fail under. He has a feeling for when the system is healthy or not. Of course, that's qualitative, that's not quantitative, and we still want to get to a point where we can measure the risk and have some degree of confidence that when we deploy an individual microservice, it's not going to break anything. So use a scoring system. Instead of trying to get an actual probability estimate between 0 and 1, just create a set of scores using your intuitions about the system and weight them. So here's a simple example of that. I can say, well, what's my unit test coverage? And I'm scoring that out of a percentage out of 100. I'm doing code reviews. So I rate my code reviews from 1 to 10. I do performance testing. I see it as a build pass. All of these things I quantify, I turn them into numbers, and then I weight them. And I see if the score at the end, which is meaningless, it's not a probability, is a number that I've become comfortable with. So in this example system, let's say I've become comfortable with the fact that a score of 0.8 or higher means that I have a very, very good probability of staying under my error rate. Well, in this case, I have a score of 0.09, so I don't deploy. And at each gate, at each stage of my continuous delivery pipeline, I score and either accept or reject. Now, you don't have to do this in Excel manually. You can build this into your continuous delivery pipeline. So when I git push a microservice, it starts a process where the microservice runs through a continuous delivery pipeline, and at each stage, tots up these numbers and gives me a score that I've calibrated using my intuition to tell me is it safe to deploy. And this is a way that you can manage the risk of deployment in a microservice system. And it's a way that you can make changes very, very rapidly. Add a feature in the morning and deploy in the afternoon, while still keeping the system up and running at an acceptable error rate. And the nice thing about this is it's a measure of reality. It removes the political dimension from deployment. It removes the blame dimension. So I find the physicist Richard Fineman extremely inspiring in this type of scenario. So what you're looking at here is a picture of the Space Shuttle Challenger just before it exploded in 1986. And you can see the arrow points at a small flare coming out of one of the solid rocket boosters. So the rubber O-rings that sealed the different sections of the solid rocket boosters failed. And that led to the explosion and the loss of 6 astronauts. In the commission, there's always a commission that followed, there was a considerable amount of grandstanding by NASA officials, where they were trying to wriggle out of the fact that they didn't really know what the failure modes of those O-rings were. And Richard Feynman, the physicist, was on that commission. And he showed, in a really beautiful way, that this really was the cause of the accident. He performed a measurement at the commission. So this is a picture of him sitting at his desk just after having cross-examined a NASA official. And he took out a cup of ice water that had a piece of the O-ring rubber in it. And he showed that the rubber deformed once it reached 0 degrees Celsius. The rubber didn't work at temperatures 0 degrees Celsius or below. And of course, on that morning in January 1986, the temperature when the Challenger launched was 0 degrees. By performing a measurement, he showed what reality was. And this idea about measuring the risk of deployment is saying, instead of having a requirement that you have to have 100% unit test coverage, because that's probably going to give you good results, incorporate things like that into a system of measurement so that you have a number at the end. And the number gives you some measure of the underlying reality, and that is how you manage the risk. Just before I go, I'm going to make a blatant plug. So I'm writing a book about all this stuff, about microservices, which kind of discusses all this stuff in much deeper detail, and also goes into a whole bunch of the other sort of risk patterns. But again, my point here, and my plea almost, is that what you take away is the idea that you can start a discussion in your own organizations about managing risk, about answering the question of how do we move faster by saying, let's aggressively measure things. Let's find the numbers. Let's get an understanding of where we are. Instead of sitting at conference tables arguing and posturing, let's put together a measurement device so that we can actually know where we stand, so that we can work with reality. Thank you very much.